Good evening and welcome to my video about iCandy Medical, a work-in-progress app. iCandy stands for the Internet's computational analysis of numerous diseases, yay medicine. So originally it was designed to be like WebMD, but instead of being for just one disease at a time, it could handle multiple diseases at a time. So we've already gone over Venn diagrams in another video. Just to show you, they are web responsive, just in case you haven't seen that video. So if you're a tablet user, 3 columns of information. Computer user, 5 columns. Very plain, very data focused, versus a balance between aesthetic and data. If you're on a smartphone and you can only handle 1 column of information, then you can handle up to 3 diseases at a time, which is enough for most people, I would hope. Neon mode, because it ceases to be intuitive after a while. Back here when we have yellow, blue, and green, it's a bit intuitive, but you get up to things like dark orange corn silk and it's no longer intuitive, so neon mode is better at that point. So, sorting out, I should probably explain something. So, if you were looking at this shape, and you know that this contains 2 different shapes forming one, what would you say that the 2 shapes are? It could be either, the video editing software I'm using is not great, but it deletes the mouse. But anyway, it could be a rectangle and a circle. It could be this, but cut in half. Or it could be, any number of shapes just overlapping each other. You don't really know what shape it is. So let's say that we try to remove, let's say that you're a doctor and you're looking for circle disease. This looks circular, vaguely. And so you find the cure to circle disease and you're left with this rectangle. So you say to the patient, well, we cured circle disease, but half of your symptoms still remain, so what did we get wrong? Did we accidentally misdiagnose you? And then this kind of messed it up. Give me a second. So, on the flip side of that, let's say that you treat the symptoms for circle disease, and you're left with this thing. So you have to ask yourself, okay, well, what is this? Is this a rectangle? Is this a square? Is this something else entirely? Just based on this, after you've treated all the symptoms, like you've taken cough drops, you've taken medicine for a fever, what is this shape? When dealing with shapes, it's actually easier than dealing with diseases, but for doctors, dealing with patients who have multiple diseases, it can be really confusing because the diseases don't really behave the way you expect them to, and it can be harder to diagnose whatever remains after you've treated symptoms. So with Venn diagrams, you can say, disease 1 causes these symptoms, disease 2 causes these symptoms, and if you were to treat disease 1, these would remain. If you were to treat, these symptoms, if you were to cure one disease or the other, these symptoms would still remain even if you'd expect them to go away after treating one disease. So that's kind of the basis of iCandy Medical, but it actually goes further than that. So I want to design this for both patients and doctors alike. So I designed a symptoms page which allows you to be either vague, like I have a cough, or specific, like I have a high-pitched brassy cough. A distinction which has a surprising difference. So a cough could mean you have the common cold. A high-pitched brassy cough could mean you have an aortic aneurysm, pulling against your laryngeal nerve, causing the high-pitched brassy sound. So this does not work because this was just my attempt at passing a very large array into an algorithm. and things did not go perfectly because I wrote this 2 years ago. But as a proof of concept of how it should work, let's look here, and you can see these buttons are the be more specific buttons. So if you say, you know, high-pitched cough, be more specific, high-pitched brassy cough, more specific, more specific, more specific. And so that's basically just the be more specific button. The way that the checkboxes work is that you have, these are basically 3-state checkboxes. So it's either yes, no, or ask my parent, or rather my nearest ancestor, I should say. So if you say I have a cough, it considers all possible coughs. If you say I have a high-pitched cough, consider all high-pitched coughs. If you say high-pitched brassy cough, it is very specific. So the difference between this and this is very significant, because if you only say, you know, consider this one, there are a lot fewer diseases which cause high-pitched brassy cough than which cause cough in general. There are a few hidden features though. So just to kind of show you real quick, if you say you have a cough, it doesn't do much. If you say you have a fever, it doesn't do much. If you have a headache, it goes into neon mode, because if you have a headache, you probably don't want to see these really bright colors. That's probably not going to be good for your headache. Also, if you say, I have a headache, just kidding, no I don't, it stays in neon mode. So it's kind of a hidden feature that if you prefer neon mode, just say, I have a headache, just kidding, no I don't. Also here on the proof of concept, this is what's called a memory form. So let's say that we have a patient who has really unsteady hands. Maybe they have a neurologic disorder or muscular dystrophy or whatever. And let's say it takes them 30 minutes to fill out this whole form, and then they accidentally hit select all. Well, that's basically 30 minutes down the drain, which is obviously not ideal. But the thing is though, is that because these are 3-state checkboxes, yes, no, or ask my parent, the ones which were yes are definite yeses. The ones which are ask my nearest ancestor, in this case, you know, asked, says, you know, bar 1 is my nearest ancestor, so I'll follow whatever he is. And then the ones who are ask my nearest ancestor, and the nearest ancestor either doesn't know, so it refers to this one, or it is this one. Yeah, you can kind of see how there's like varying degrees of specificity. Another example of why this is important is, let's say that instead of going through and, you know, saying select all except these, let's say instead of doing that, you did something like this. Deny, 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 and deny, and then consider all the rest. So that's another way that this works. So it helps people with muscular disorders so they don't accidentally lose all their progress. And it also helps people who do things differently. I'm a firm believer that web developers should adapt to all users. Like, you can't just, well, I mean you can, but you shouldn't just have one way of doing things and expect all users to follow it 100%. Like, when it comes to medicine, this is like a 20-step process. And if I just said, okay, you have to do all 20 steps perfectly or else the system fails, you're going to have a lot of failures in that case. So I do try to adapt to all users, and I did go the extra mile here to make that the case. So another hidden feature. You can see I took color blindness into account. So if you want to see the color wheels real quick, these are what the this is normal vision versus red-green color blindness versus red-green color blindness versus tritanopia, which is blue-green color blindness, I believe. So in making something that works for, that creates a gradient for people of all sorts of color seeingness, of all forms of vision, I came up with this. So it looks kind of like a sunset to people with normal vision, and it also looks pleasing to people who are slightly colorblind. So now on to the results page. So we already demonstrated earlier that if you are very specific, you can narrow down your possibilities very easily. Versus if you are not very specific, you might have to go through a process of elimination. So that's what manual here is. Automatic is still kind of scattered. I'm sorry for that. But manual is like the process of elimination to help narrow down your search even further. So here you can confirm or deny different diseases or disease categories. So like for me, for example, I am a male, so I don't have to worry about female-specific diseases. Verification steps are like if you have 500 bacterial diseases under consideration, 500 viral diseases under consideration, and 1 cancer under consideration, you can narrow your search down a lot more by determining whether you have a viral disease or a bacterial disease. So verification steps is designed to help you narrow down your search as much as possible after you've confirmed or denied diseases. Edit search, not working, and I honestly have no clue where to start with this. Compare multiple diseases. That goes back to the Venn diagrams we showed earlier, and how you can compare different diseases together like that. So the only thing I really have on this page particularly is not a whole lot. So there's this. If you click on the question mark on the right, it brings up information about a disease. And actually, just realized I have no way to close it. Okay, there we go. So you have 4 options for the checkbox on the left. You have yellow, which is I don't know, and that's the default. Green, which is yes. Grayed out, which is no, I do not have this disease. And blue, which is prioritize this disease. And once again, with the checkbox, I tried to take colorblindness into consideration by having a check mark next to yes, I have the disease, and a check mark next to yes, prioritize, versus no, I don't know, and no, I don't have it. Let's just keep this yellow for now. So here we have symptoms, common symptoms, and if the patient has those, then they can move on to may also cause. And if they have those, they can move on to occasional symptoms. So the reason why I separated these out so much is to account for hypochondriacs. So if a patient, let's say that lung cancer might occasionally cause you to have itchy eyes. A hypochondriac might come in and say, oh, I have itchy eyes, therefore I must have lung cancer. And to protect against that, we show the common symptoms first, because these are the more important ones, and then you may also want to watch out for, these symptoms. Discrete symptoms. These are for doctors, and doctors have more discretion. I hate using that word twice, but they have more discretion when looking at symptoms. So for them, we show all of them at once. So these are things like low blood sugar, things which you wouldn't necessarily notice automatically, but which a doctor might find useful. So here we have noticeable symptoms like I have a cough, I have a fever, I'm sneezing. Discrete symptoms are things you can't really see, like an immune problem, etc. So verification steps. So these verification steps are for a single disease. This is like you can narrow out one disease at a time. So if you're like really laser focused on one type of disease, you can test for it. So in this case, we use one verification step is extremely simple and one is extremely complicated. So blowing your nose into a Kleenex is on top because it's the most cost effective. It's cheap, and depending on the color of your mucus, you can rule out potentially half of all diseases. Versus getting an autopsy is very expensive and also not great in most cases. Like if you have the common cold, getting an autopsy wouldn't even reveal that. So diagnosis criteria. So diagnosis criteria is kind of like a point system. So like lupus, for example. Lupus has 3 major symptoms and 10 minor symptoms, if I remember correctly. And you have to have 2 major symptoms and at least, I think it's 5 minor symptoms, if I remember correctly. So that would be a major and minor type of point system, where you have to have 2 out of 3 in category 1 and 5 out of 10 in category 2 in order for it to be considered lupus. They also have major or minor type point systems, where it might be like the major symptoms count for 3 points and the minor symptoms count for 1 point each, and you have to have at least 11 points to be considered having the disease. Of course, simple is like, each symptom is worth 1 and you need at least 4. That's pretty simple. Pure or, what was this one? Oh yeah, so there's the pure or point system, where there are potentially multiple different ways to diagnose a disease. There might be subjective evidence, which would be a subjective diagnosis. There might be clinical, which is like, you definitely have symptoms, you saw a doctor, which would be, again, a subjective diagnosis because you don't know for sure. And then there might be laboratory diagnosis, where you send your blood into a laboratory, they test for the disease, and they prove that you 100% do have the disease. So that would be an objective diagnosis. Some but not others. So this is a type of point system where some symptoms add points and others take points away. It's been a while since I've looked at this. I apologize for that. Acquire additional information. Okay, so I have a really bad habit of starting with the most complicated things first. So let me quickly, where's my keyboard? Okay, so this is a representation of a diagnosis of an exponential complex. So exponential complexes are whenever you have 2 diseases which are relatively okay on their own, but put together they make each other exponentially worse. So I don't really want to talk too much about a certain type of disease. So like, let's say you have an immune deficiency plus an infection. Immune deficiency is fine as long as you don't get infected, and infection is fine as long as your immune system can handle it. But the worse that your immune deficiency is, and the more severe that the infection is, the exponentially more severe the situation becomes. And so you may be wondering, what's the difference between blue and green? So blue is subjective evidence. And by the way, in coding this, I made this using ClipPath. So if we look at the code real quick, well, hopefully. Oh, yep, there we go. So Give me just a second. Alright, so the blue is subjective evidence. So, like, based on subjective evidence, we believe that, you know, your immune deficiency has 50% severity. Versus, you know, here on the left side, we sent your blood into a lab. The lab confirmed that you do have infection, you know, infection X, let's call it. And so there is objective evidence that you have it. So objective evidence is green versus subjective evidence is blue. And then the kind of fading areas are the margin of error. So here at the tip, the fading blue, that is the maximum severity which we think you have based on objective plus subjective evidence. Green is the minimum that you have based on objective evidence. So this kind of shows both the minimum severity, the minimum possible severity, versus the maximum possible severity based on subjective evidence. And so exponential complexes are probably the most complex subject in medicine, but I wanted to start with them because I kind of hate starting with the easy things first, because if you start with the easy things first, then you move on to harder things and you realize that the methods that worked for the easy things don't work anymore for the hard things. So I wanted to start on the hard thing first so that the easy things would definitely work with it. So what this does is it has linear gradients, and it's actually written directly into the HTML itself. So you can kind of see, if you look on the right side of the screen, you can see background image, linear gradient, to top, green, yellow, 0%, etc. And then, where is clip path? Clip path is on this one. So, if you look at it for a while, I'm not going to, go back and forth between, linear gradient and clip path, but if you look at them for a while, you can see that a lot of the numbers match up. And in terms of code, there are values of like minimum objective, minimum subjective, etc. And those are given values. Those values are plugged into a linear gradient and clip path, and together they form the exponential complex thing. So next is stop the spread. So this just tells you how the disease is spread, what to do, and what not to do. Treatment options. So this is where things get really complicated. You can probably see that by the colors. So if it's green on the left, that means it's safe for you. If it's yellow on the left, that means it's experimental for you. If it's red on the left, that means it's dangerous for you. So you may be asking, okay, but Colton, if a treatment is dangerous, why would it be on the market in the first place? Well, think about penicillin, for example. Penicillin is an antibiotic which is safe for most patients. But if you're allergic to penicillin, it might be dangerous for you. Another example of things that might be dangerous for certain people. Let's say that you have a really weak liver for whatever reason, and you need a surgery. The surgery might be fine, but the anesthetic that they give you for the surgery might knock out your liver if your liver is on its last leg. So understanding the organ function of a patient can be important for things like that. So allergies, organ function, and I'm not actually sure what else. I haven't been studying this part of medicine for too long. But on the right side, we have the credibility of a treatment. So I don't really want to go too deep into the difference between FDA cleared versus FDA approved, but the colors kind of speak for themselves. FDA cleared is, well, FDA approved is not great, and FDA cleared is really not great. You want something to be tried and true. So it must have been on the market for at least 5 years. No major complaints, no perforated organs, nothing like that. So, safety on the left, credibility on the right. And if anything's tied for safety and credibility, then it goes to being based on cost effectiveness. And if someone is colorblind, we have these little stamps on the right, which are like A+ for safe and tried and true. And then you have the effectiveness right underneath it. So you may say, okay, well, why does effectiveness need to be on the very top layer? So cost effectiveness is like getting, the most bang for your buck. So like, if you had to pay $10 to get rid of 50% of your acne, or $10,000 to get rid of 100% of your acne, you're probably not going to pay that extra $9,990 just to get rid of another half of your acne. Like, that's just not cost effective. But on the other hand, if you have brain cancer and your options are $10 to get rid of half of your brain cancer, or $10,000 to get rid of 100% of your brain cancer, you're more worried about being 100% effective than you are about, saving a few $1,000s. So for some people, effectiveness is all that matters, so we want to have effectiveness on the very top layer. So these treatments, they have descriptions, they have effectivenesses, follow-up procedures, costs, possible side effects, implications of those side effects, etc. Additional resources like videos about the treatment, articles about the treatment, and there's a lot of information about each treatment. I would like to add more, but I'm not sure what else to add yet. I do want to say, by the way, that this is actually formed from an actual object. Like, a random disease has its own object, and it was actually parsed into a template. Like, this is all data that's actually in an object. It's actually been parsed. These treatment options have actually been sorted. They were not originally sorted in the object, but the program auto-sorted them. And you can see the numbers to show like how they're supposed to be sorted. Make sure they're actually sorted the right way. Tools, advice, etc. So these are things that a patient might not need, but that they might want. So like, let's say you don't need to have an electric wheelchair, but it might be helpful. Or, so let's say that maybe you have muscular dystrophy, and you can't really pick up a gallon of milk anymore. There are a lot of soap bottles have those little pump things. Like, hand soap has that little pump where you push down on it and it squirts soap into your hand. They have that for gallons of milk and gallons of tea. So you might want to get something like that so you can just kind of, pump milk into your cup rather than having to lift up the gallon each and every time. So that's a helpful tool. Places to live. So, like, let's say that you are in a wheelchair. You want to live in a place that has a very robust public transportation system. You probably don't want to live out in a rural area where there's no public transportation whatsoever, no way to get around. That's not a good idea. But in urban areas and suburban areas, you can order food with an app so you don't have to get out. And public transportation is often wheelchair accessible. So places to live can be important depending on what disease you have. Additional resources, so these are things like food allergy support group. Advice. Some NSFW advice. So it's not shown originally, but you can click on it and it will show it. Because medicine does get NSFW sometimes. So automatic. now is where we get into some math heavy stuff. So what should we start with? So let's start with this actually. Alright, so let's say that we're comparing 2 diseases at a time. Let's say we start out with 6 diseases under consideration, and we're comparing 2 at a time, right? So, first of all, you don't want to compare 1 versus 1 because that would be redundant. 2 versus 2, redundant. 3 versus 3, redundant. Also, 1 compared to 2 is the same as 2 compared to 1. So those are redundant. So overall, this starts out as x squared minus x all divided by 2. An easy way to do this is just to have a nested for loop and have I start out as, excuse me, I need to get a drink of water, and have I start out as I plus 1. That way, if I is 1, I will start at 2. If I is 2, I will start at 3. If I is 3, I starts at 4, etc. So already, just based on that, we have this, x squared minus x all divided by 2. But when you're comparing more than 2 diseases, like let's say we're comparing 3 diseases. So it's easier to use this notation of x times x minus 1 times x minus 2. So the first disease, you can choose basically any disease, theoretically. Disease number 2 can be any disease except for the first, hence x minus 1. The third disease can be any disease except for the first 2 that were chosen, hence x minus 2. And when comparing 3 diseases at a time, there are 6 permutations for each unique combination. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. 6 permutations for each combination. So instead of being divided by 2, to account for redundancy, it's divided by 6. And when comparing 4 diseases, it's divided by 24. 5 diseases, 120. 6 diseases, 720. And now let's talk about factorials. So before we get into the nomenclature, the abbreviated nomenclature, we need to talk about factorials. So a factorial is a number times 1 less than itself, times 2 less than itself, times 3 less than itself, times 4 less than itself, etc. Which is very much what we have up here. So if a factorial stops being divided or multiplied by more numbers, it can often be considered a factorial divided by another factorial. So in this case, factorial 10 divided by factorial 5, the 5 and 5 cancel out, 4 and 4 cancel out, 3 and 3 cancel out, 2 and 2 cancel out. You're left with 10 times 9 times 8 times 7 times 6, because everything else cancels out, which is very much reminiscent of what we have up here, where you have, let's say, x equals 10, 10 times 9 times 8 times 7 times 6, and then we're comparing 6 diseases, so this would be times 5 as well. And so it's considered a factorial divided by another factorial. So the ultimate nomenclature is this. The factorial of x minus d minus v divided by factorial of x minus d minus c multiplied by factorial of c. So c is the number of diseases under consideration, x is the number of diseases we start with, d is the number of diseases we've denied, and v is the number of diseases we've verified. So remember back in results, we could confirm or deny diseases, that has implications algorithmically. So, real quickly, let's talk about C. So, let's assume that D and V are both 0 right now. Let's just talk about C. So, factorial x divided by factorial x minus C. So it's kind of like this right here. So let's assume that C is 5. We are considering 5 diseases at a time, right? Let's say x is 10. So 10 times 9 times 8 times 7 times 6, and then it stops there. So, or actually let's consider x to be 20. So 20, 19, 18, 17, 16, and then, so that's basically factorial 20 divided by factorial 15. So if x is 20 and c is 5, you can kind of see here that the factorial of x minus c, x is 20, c is 5, that would be factorial 15. So on top, factorial 20, on bottom, factorial 15, which is how you get this. And then times c, times factorial c at the bottom, that's again, 5 diseases under consideration, that's the 120 right here. So what are D and V? D means that something was denied, and let's quickly ramp C up to 6. There we go. So D just kind of moves everything horizontally along the x-axis because it only affects x. Now V is an interesting case because with V, you kind of have one less disease to consider because it's considered on all combinations. So like let's say that we have 3 diseases, 1, 2, 3, 4, but 4 is confirmed. So now we have 1, 2, 3, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, and then add 4 to all of them. So effectively, algorithmically, 4 is no longer combinable because it's part of every combination. It's like a prerequisite in a way. So that's why that's why V is subtracted from X, but it also takes away from C, the number of diseases under consideration. Because let's say that we are considering 6 diseases at a time, but 5 diseases are already confirmed. That means 5 slots of the 6 are already taken up, which means that there's only 1 slot left, which means that it's only, like let's say we have 4 diseases left. It can either be add 1, add disease number 2, add disease number 3, or add disease number 4 to that last slot. So it takes away from the number of slots available, which effectively takes away from C. So you can see if we change V to 1, and then let's say we make D hypothetically, well, did I write this wrong? I apologize. My browser crashed earlier and I had to rewrite this. I may have written it wrong. Let's see, x minus c, c minus v. Is it? I think I messed up here. There we go. Yeah, that's how it's supposed to work. Let's say that D is minus 1. You can see that, that this equation where C is 6, V is 1, and D is hypothetically negative 1, this matches up now with comparing 5 diseases at a time rather than 6. So if V equals 2, and let's say D equals negative 2 just to balance it out, Oh, these are the exact same color. That's not helpful. But yeah, you can see that now even though C is 6, it matches up with as if C was 4. Let's go ahead and change this back to 0 just to kind of distinguish them a little bit. So yeah, now you can see that it works as if C was 4 because B is taking away its slots from C. So there's actually 2 more types of redundancy though that we need to talk about. So this green thing here, this is what's called satisfaction redundancy. So let's say that disease 2 plus disease 4, wait, am I still recording? It's not showing up on, okay, yes I am. So let's say that 2 plus 4 satisfies all of the patient's symptoms. You could also say that disease 2 plus disease 4 plus disease 5 satisfies all the patient's symptoms. Disease 2 plus 4 plus 6 is satisfactory. 2 plus 4 plus 5 plus 6 is satisfactory. Already that's getting really annoying, right? So instead of saying 2 plus 4 plus 2 plus 4 plus 5, you say 2 plus 4 and maybe more. And you condense all those other things into, yeah, just 2 plus 4 and maybe more. On the flip side of that, you have the diseases which come before them. So you could say 2 plus 4. You could also say 1 plus 2 plus 4, 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4. That's already getting really annoying with just 6 diseases. So, but there are different ways to handle these types of redundancy. So with satisfaction redundancy, all you have to do is say, okay, stop calculating. So if I show you the code real quick. Do I have it? Do I not have it? Do I seriously not have it here? Okay, well apparently I have to go looking for it, but yeah, no, it's not. Is this it? No, that's not it. That's not, is it in Cravens? It's not there. Okay, well, I thought I had it pulled up, but apparently not. But basically, you say, okay, so 2 plus 4 is satisfactory. Don't consider anything after this. You know, don't consider 2 plus 4 plus 5. Don't consider 2 plus 4 plus 6. This is easy because we use a branching object. So it starts out as 2, then goes on to 2 plus 3, then 2 plus 4, 2 plus 5, 2 plus 6. And then 2 plus 4 turns into 2 plus 4 plus 5, 2 plus 4 plus 6, etc. And so it branches out the more combinations or the more diseases you are considering. So all you have to do is say, okay, 2 plus 4, stop considering. You know, display your results and stop considering anything else. You are 2 plus 4 plus more, potentially. But it's not so easy if something kind of sneaks in from the beginning. So like, if 1 plus 2 plus 4 is satisfactory, you can say 1 plus 2 plus 4, stop considerations, but that's still redundant. And it can be really annoying if you have 20 diseases. Oh, that's not right. So we have to use something called backtracking. So backtracking is a 4-step process. So going from left to right, you have the diseases with their symptoms, and it's put into a 2-dimensional matrix. From there you have from bottom to top. You count the number of symptoms, and you get this number on top. And I'm pretty sure that my recording software deletes my mouse. I apologize for that. So it counts the number of each symptom. And then it returns those numbers back to the 2-dimensional matrix. It goes from top to bottom. And then it checks to see which disease is a contributor. So in this case, A is the sole contributor of the first symptom. C is the sole contributor of the final symptom. B, on the other hand, offers nothing unique to this combination. So A plus B plus C can also be described as A plus C plus more. And backtracking can actually be used preemptively. Like, you don't have to wait until you get to, A plus C is, or, all these diseases together are satisfactory. Now let's backtrack. You can actually do it preemptively and save yourself a lot of operations that way. So you can kind of see here that operations kind of get out of control. Let me move this back and like this. Kind of get out of control pretty quickly if you allow them to. So backtracking and kind of cutting off those branches as soon as possible, as soon as you possibly can, as soon as there's any sort of redundancy, is really important for efficiency. Let's see, what else was there? I've already gone over. So there's one more thing I want to add to this. Actually, I don't want to talk about future features, but that's another 20-minute video right there. Yeah, this video is already long enough. This is all I've worked on so far. Again, studying medicine does take a long time, so the studying has definitely taken a lot longer than the coding. But yeah, this is a work in progress. Again, it is designed for patients with multiple diseases. It is web responsive. It is designed to be as vague or specific as you need it to be. We do take headaches into account. It uses a memory form. We take color blindness into account. I say we, it's just me. And there's a lot of math involved. And also a lot of really advanced stuff for the patients with really rare symptoms, or rare diseases I should say, and rare combinations. And yeah, as the name implies, Internet's computational analysis of numerous diseases, yay medicine. This app was originally designed to be simple. It was originally designed to just have Venn diagrams, and that would be it. It would be WebMD, but for multiple diseases at a time. And instead, it's kind of exploded into a one-stop shop for all things medicine. In fact, one thing I'm planning to add is something called comprehensive banking, which is something I'll get into in another video. But yeah, this project has definitely grown in scale from when I first started it. Again, my name is Colton Hatley. I am available for hire, and I apologize that this was more math and medicine than coding. But yeah, it's a complex problem. The code is the easy part here. Again, Colton Hatley, available for hire. Have a good evening and Happy New Year.